whiteboard up. Start. Okay. What's the slide? Okay, so last time, I'm just going to continue where we left off last time. We were talking about, this is just a review of power series. And so I'll continue to talk about some properties of power series. We had talked about addition and subtraction, multiplication, division, as long as the constant term A0 is not 0, or it's not equal to 0 at its center. So a few more properties. Let's see. So if we have a power series, yeah, that's not going to work. Clear that. All right, that should be good. All right, so we have a power series which we're calling f of x, a0 plus a1x plus a2 x squared plus a3 x cubed, and so on. Or let's include. I'm going to write it out like this, and then I'll explain why I might skip writing it out like this. So this is the more general way to write this. Okay, so this is a power series, a general power series centered at x equals x0. We can always shift a power series to the left or right by changing where it's centered. Well, we end up with a new function, but if we have a power series centered at 0, then what we would have is a0 plus a1x plus a2x squared plus and so on. So in general, we can talk about the power series centered at 0, and then everything that we know about that transfers very easily to a power series centered at any other value of x. Okay, anyway, we have a power series, then f is continuous. It's differentiable, so f prime exists and is continuous. And in fact, every derivative of this exists and is continuous. So we can take the derivative arbitrary number of times. So all of these derivatives exist. And we have a very straightforward way of determining what the derivative is. So if this is our power series, then its derivative we do just termwise using the power rule, or whatever we call that derivative. So f prime of x, we'll just take the derivative termwise, and it'll be derivative of a0 will just be 0. The derivative of a1 with respect to x will just be a1. And then a2 will be, write it, 2a2 x minus x0 plus 3a3 x minus x0 2. So the 3 comes down in front, and then the exponent goes down by 1, just like before. And the arbitrary term will be n times an x minus x0 to the n minus 1. And this continues on. So the derivative is exactly what we would think it would be. And so the way we write this is, well, first of all, reminding ourselves of the sigma notation here. This would be the sum from n equals 0 to infinity of a n x minus x0 to the n. Taking the derivative of this, we get the sum from n equals 1 to infinity. We're going to, when we take the derivative, this constant term is going to go away. N a n x minus x0 to the n minus 1, which is pretty easy to see just, by applying the power rule to this arbitrary term here, the general term. Okay, so in a similar way, we can get the second derivative. Second derivative of x will be 2a2 plus 3 times 2, a3 times x minus 0, plus, and now we didn't write down the next term, but when we took the derivative, we would have a 4a3, and so we would have a 4 times 3, a4, sorry, a4, not a3, x minus x0 squared plus 5 times 4, a5, x minus x0 cubed plus dot, dot, dot. And the general term will be n times n minus 1, a n, x minus x0, n minus 2. So writing it in sigma notation will be n, of course, continues on like that. N times n minus 1, a n, x minus x0 to the n minus 2. And now our numbering will start from 2 instead of 1. We can continue this process for as many derivatives as we need. And each of these has the same absolute convergence. So if f converges absolutely for some radius, so some distance from the center is less than rho, then f prime, well, any derivative of f, so I'll just write that, converges absolutely in the same radius. So when we take the derivative, we don't change the radius of convergence. I think it is possible for the convergence to change at the endpoints, but it does not change in the region where it converges absolutely. Okay. Now, if we have a function, so first we have two directions. We can either say that we have a power series like this, and we figure out where this power series converges, and we declare that f is a function, that the output of the function is whatever the output of this power series would be. So we can take a power series and we can declare a function based on that power series, or we can go in the other direction. We can say that if f is some function with all derivatives defined, so it's continuous, it's differentiable, its first derivative is continuous and differentiable, its second derivative is continuous and differentiable. We can just keep taking derivatives over and over and over forever, which is like most functions that we know. Then it can be represented, or we can write it as a power series. And this is called its Taylor series. You might remember this from talk 2. And in fact, we can figure out a Taylor series for it. So if we know where this function is centered, so let's say where we want the power series to be centered. Let's say we center the power series at x0. Then if we plug in x0 and we try to determine what the power series would be, so it will be represented by some power series. We're just trying to figure out what a power series that represented would be. We would have something like this. This is a power series centered at x0. Then this is 0, this is 0, and everything else is 0. And all we're left with is a0. So we know that a0 is equal to f of x0. Now, because we said its derivative was defined, we can determine what the value of its derivative is at this 0, or that at the center, sorry. And so f prime of x0 would be equal to, now when we take the derivative, the a0 goes away. The derivative of this term will just be a1 plus something, let's write a box, times x minus x0 squared plus something. We know what that something is, but you don't need to bother writing it out. Sorry, not x squared times x minus 1, or x minus x0 squared, x minus x0 cubed, and so on. And of course, again, all of these go to 0. And so what we're left with is just a1. And so a1 is equal to f prime of x0. Well, maybe it would be useful to write in what it should be. So we took the derivative, that's a1 should be 2a2, 3a3, 4a4, n x minus x0 to the n minus 1, so on. So if we want to get a2, we just do this again. Take the derivative again. The a1 will go away. We'll be left with 2a2 plus 3 times 2a3, x minus x0 plus 4 times 3a4. You can see the pattern. One more just for the sake of illustration. So we get this. Again, all of these go to 0. We're just left with 2a2. And so we get that a2 is equal to f double prime of x0 over 2. The next time we did this, we would get 3 over 2, or divided by 3 times 2. The next time we would get 4 times 3 times 2, and then 5 times 4 times 2. So let's write a few of these out just to see the pattern. F triple prime x0 over 3 times 2. A4 be f, I'll write quadruple prime, maybe we should switch to writing the number just in parentheses next. So that's what we get for A4. And then one more for A5. We can see, we're seeing how this pattern is going to play out. I'm going to write a times 1 in there. No harm in doing that. Anyway, it makes it clear what's going on with this. We continue in this pattern, what we get that AN is equal to the nth derivative of f evaluated at x0 divided by n times n minus 1, n minus 2, times 3, blah, 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 down to 3 times 2 times 4. And that is, of course, in factorial. Now, we want to make sure this fits with the previous ones. So it fits perfectly with all of these. Let me see how this process works. Now here we have the first derivative of f divided by 1 factorial. And that's fine. 1 factorial is just 1 times itself. But we do get into a little bit of a strange situation here. We have to say that the function itself is the 0th derivative. That might feel kind of weird, but let's say we have no problem with that. We're taking no derivatives, so that's the 0th derivative. 0 factorial, however, in this case, is going to have to be equal to 1. So we're going to have to say that 0 factorial is equal to 1. And this is the convention that people adopt for saying what is 0 factorial? Well, it's I apologize, I got distracted by my phone. I'll turn it upside down. We can think of 0 factorial as sort of the empty multiplication. What happens when you don't multiply anything? I won't try to justify it beyond that. I'll just say that this is the convention that people adopt. In part because of this formula right here that we get for the coefficients of the power series, or for the Taylor series. So if we have a function and we declare that for some region around x0, this power series will represent f of x, then what we get is the sum from n equals 0 to infinity, the nth derivative of f, keeping in mind the convention that the 0th derivative of f is just f itself, divided by n factorial, keeping in mind that 0 factorial is equal to 1. Then this is the this would be the Taylor series representation of the function. And we would have to say, what is the radius of convergence of this power series? And so this function, we would have to say, we only define it inside the region of convergence. Because outside of that region, we don't define this power series as actually having a value. If it doesn't converge, then we're not going to say that it's equal to anything. Oh, sorry, I left out the x minus x0 to the n part. There we go. Okay, so this is how we get the Taylor series representation of f. And it might be useful to just have a reminder. You've seen these before in Calc 2, but it might be a useful reminder to go through getting the Taylor series representation of some famous function. So for example, if we wanted to do sine of x, and we want to center it at 0. So if you remember, this is called I'll just say the name, I won't write it down. When the Taylor series is centered at 0, it's called the Maclaurin series. It's sometimes a nice place to center your power series, and so why not? Okay, sine of x. We know how the derivatives of this go. Let's just evaluate. Well, let's see. This is the thing that we're trying to write. So let's evaluate sine of 0 at our center. And its first derivative is cosine. So we'll evaluate cosine of 0. Now the derivative of cosine is negative sine. And the derivative of negative cosine is negative, or negative sine is negative cosine. And then we get back to the next one is sine of 0. So the fifth derivative is the 0th derivative, or sorry, the fourth derivative is the 0th derivative. So if we can evaluate these 4 right here, then we'll know all of the derivatives that we need to know in order to determine the Taylor series, or the Maclaurin series in this case. So sine of 0 is equal to 0. Cosine is equal to 1. Negative 0 is 0, and negative 1 is negative 1. And so what we get is that for our Taylor series, we will have 0 for the first coefficient, 1 divided by 1 factorial for the, say, the 0th coefficient, and 1th coefficient of the first coefficient. 1 divided by 1 factorial, that's just 1 times x minus x0. Well, x0 is 0, so it's x. The n, which is just 1. Now the a2 will be 0 divided by 2 factorial, so that's 0. And the next one will be 1 divided by 3 factorial, which I'll just write as 3 factorial, but of course that's 3 times 2, so 6. X cubed. Now the next time we get to a non-zero one will be the 5th one. So this will be plus x to the 5th, or 5 factorial. And then the next non-zero one will be negative 1, so it's minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, so on. And so this is how we get the Taylor series representation of that, of sine of x. Now I'm going to, I'll do a derivation of the Taylor series for e to the x. As soon as I take a quick drink of water. And I'm going to do this one in a little different way. So if we have, nope, come on. Yep. Only a few more weeks. Only a few more weeks. We're done. A couple more weeks. Maybe if I do it like this. Okay, that's probably good. E to the x, its derivative is e to the x, and its derivative is e to the x. So it's even easier in this case to figure out what the values of the derivatives would be. So if we wanted to plug it into this formula, we would just get e to the x is equal to f, any derivative of f evaluated at 0. So we're going to center this at 0. I should write that down. Any of the derivatives evaluated at 0 is just 1. And so we get from this that the Taylor series representation is just 1 over n factorial times x to the n. So I'll just write it as x to the n over n factorial. We could do this a little bit differently. So let's say that we came at this from a different angle. We didn't go through all of this reasoning to find an explicit formula for the Taylor series. We'll just say that e to the x is equal to a0 plus a1x plus a2x squared. So just some arbitrary power series centered at 0. And its derivative, well, let's write this in sigma notation first of all. N equals 0 to infinity, a n x to the n. And then we say it's equal to its derivative. So if we take the derivative of the power series, what do we get? We get a1 plus 2a2x plus 3a3x squared plus and so on, which is equal to sum from n equals 1 to infinity a n a n x n. Now, I will have to introduce one fact in order to do this. So I got this a little bit out of order. But this is a very important fact for power series. It's related. There's a related fact for polynomials, so it carries over in a very nice way. And this is going to be very important for the method that we're going to use for using this to solve differential equations, power series to solve differential equations. And that is that if we have two power series, say an x minus x 0 to the n, and we have another power series, n equals 0 to infinity, bn x minus x is 0 to the n, and we say these two things are equal to each other. So these two power series, whenever we can plug in a value for x, we get the exact same thing. And what we have is, in fact, that these two power series have equal coefficients. Right? And the same thing works for polynomials. We have two polynomials that are equal to each other, then their coefficients are equal as well. And that was what we used for a method of undetermined coefficients, for example, whenever we wanted to get a particular unit. So we'll do a similar thing with power series. And so we'll need to know that we have two power series that are equal to each other, then their coefficients are equal. And that justifies us in saying that whenever we say, I go back to this statement right here, I said this was a Taylor series representation of F. Now, we decided from this that we could compute a Taylor series representation. And because we know all of the coefficients, if we had any other Taylor series representation centered at the same value of x, then it would have the same coefficient. So it would be the exact same Taylor series. So instead of saying this is a Taylor series representation, I will say this is the Taylor series representation. So it's unique. All right. Now we'll use this to figure out how to do e to the x. Actually, let's do a couple of other examples first, and then we'll come back to this. We're going to say these two things are equal to each other, and then we'll figure this out. Okay, so let's do some examples. Okay, now here's the first, and this is a completely trivial example, so this should be obvious. If we have a power series, let's say the terms are 2 to the n, x to the n over n factorial. This is some power series. There's nothing special about that, the index variable n. It's just a letter. We just chose n because I guess it's short for number. There's nothing special about it, and so we could just change that variable and just say j instead, right? Now, at this point in our mathematical lives, we're sophisticated enough to say these letters don't have any intrinsic meaning. We can substitute any letter. In fact, we've done that a lot so far in this class. What's a little more interesting is that we can take a power series like this. Let's say this is a power series, but the indexing starts at 2. So we're assuming that a0 is equal to 0, a1 is 0. And we want to change the index variable, not just what the letter is, but where it starts. So we want to make this thing so it starts at 0. So I'm going to change the indexing variable so that it starts at 0. And we'll use another variable. We'll call it m. Now, what kind of change are we making here? When m is equal to 0, n will be equal to 2. So what we get is that n is equal to m plus 2. this kind of change of variables, the same kind of change of variables that we would do for integral. An interesting aside, the integral symbol that looks like this looks like an elongated S. It actually is an elongated S. It's supposed to stand for sum or summation, just like the capital sigma in the sigma notation. There's the connection between those two goes a little deeper than I'm making it seem like now. Anyway, the upper limit would be infinity. When it's n, it's equal to infinity. So m would be infinity minus 2, which is, of course, still infinity. And when we replace n, we'll replace it with m plus 2. This is a simple first example of changing our, shifting our index of iteration when we're going through the summation. So we basically just, since we're starting from 0, we've compensated by increasing that thing by 2. So it should have started from 2. We should have had our first term as a2. And so if we start indexing from 0, then we want these values to start at 2. It's a good way to check that. Okay, slightly more complicated example. Start from 2, go to infinity, n plus 2, n plus 1, a n, x minus x0, the n minus 2. And we'll say that we want this to start. Well, let's look at it a little different. The power of x minus x0 to the n minus 2, we want to alter this so that the generic term, the power of x minus x0, is in fact to the n instead of the n minus 2. This is a step that we'll use later on in order to compare these things. Okay, so what happens when we do this? Well, if we want to introduce a new variable, index variable, we'll call it m, and we want it to be equal to n minus 2, we can do this. And so what do we get? Well, we will replace n with m plus 2. And so that allows us to say if n is equal to 2 and m is equal to 0, that's where we'll start. Infinity, well, we need to replace infinity with infinity minus 2, so infinity. Now n plus 2. N plus 2 will be n plus 4. N plus 1 will just be n plus 3. Nothing groundbreaking happening there. N in the an here will be am plus 2. And then x minus x0 to the n minus 2 will be x minus x0 to the n. So we did kind of one step here where we did a change of variables. Here's the index variable. Now we can do one more step and say, for the sake of things looking nice, we want to go back to using the index variable of n. And we're using m right now. There's nothing special about m. We can just replace it with n. So we can do this. Replace the m. And this would be re-indexing this series so that the generic term has a x minus 0 to the n instead of x minus 0 to the n. This will be an important step for doing. Now we did it in 2 steps, and you'll probably notice right away that that was unnecessary to break it up into 2 steps. We could have just done it in 1 step. Let's go straight to using n starting from 0 instead of starting from 2. So that's what I'll do from now. Okay. Moving up slightly in the level of complication, which 3 minutes. Okay, so n equals 0 to infinity. This is actually going to have an x squared multiplied out front. R plus n, a n, x to the r plus n minus 1, where r is just some arbitrary constant. And we want to rewrite this thing so that that x to the r plus n minus 1 is rewritten. We re-index it so that the exponent is just r plus n. Okay. So how can we do this? Well, the first thing I'll do is move the x squared in. So if I do that, multiply x squared by every term. Of course, that involves an assumption that this series right here actually converges. So it only works where it actually converges. But that will be r plus n times a n, x to the r plus n minus 1 plus 2. So that'll be r plus n plus 1. Now we want, instead of r plus n plus 1, we want our generic term to be r plus n. And so we're going to, instead of starting from n equals 0, we'll start from n equals 1. We'll have r plus n minus 1 to compensate for the indexing going up by 1, a n minus 1. And now when we replace n with n minus 1 in the exponent here, we could just get r plus n. And that gives us our re-indexed power series with a x to the r plus n. Now, the last example that I'll do is actually applying this. An interesting case. Actually, let's go back to the e to the x case. So let's say e to the x is equal to a0. I'll just write it. Sum from n equals 0 to infinity, a n x to the n. And it's also equal to its derivative. So its derivative will be, we start from 1 higher. We have n, a n, x to the n minus 1. There goes my timer, so I'll try to do this quickly. I'm not late for my appointment. But if we re-index this thing so that it starts from 0 instead, then n will be replaced with n minus 1. A n minus 1, x to the n. Now, what was useful about this is now the coefficients line up. We have coefficients on x to the n here, and we have coefficients on x to the n here. And so we can say, by that previous fact that we talked about, a n is equal to n minus 1 times a. Did I get that right? No. It should be n plus 1. Mixed it up. You can always check and make sure that you're doing this right. So when we start with n equals 1, we should have 1 times a1 times x to the 0. So here, when we start from 0, we want 1 times a1 times x to the 0. So with n plus 1, that works. So we get n plus 1, a n plus 1. And we can also re-index this. It's kind of easier to say what a n will be in terms of the one before it. So we can say a n minus 1 equals n times a n. So doing that re-indexing is a little bit easier. And then we'll say that a n equal to an minus 1 over n. Now, all that we have to do is figure out what a0 is, and we can do that by just plugging in 0 into the function because it's centered at 0. So we'll get that a0 is equal to 1. And then a1 is equal to a0 over 1, which is 1. And a2 is equal to a1 over 2, which is 1 over 2. And then a3 is equal to a2 over 3, which is 1 over 3 times 2. And then continuing in this way, 1 over 4 times 3 times 2. a5 is equal to 1 over 5 times 4 times 3 times 2. And I'll stop belaboring the point now and just say that a6 is 1 over 6 factorial. a7 is 1 over 7 factorial. And continuing in this way, we get 8 1 over n factorial, which is just what we got before. Okay, so this is just a quick example of doing this. Tomorrow, we will start looking at actually using this to solve differential equations. And on that note, I will end for today, unless you have any questions. Questions? Nope. Okay. I'll see you tomorrow unless I have problems getting on the internet while I'm in. Have a good day.